In 2010, the SEC used statistical hypothesis testing to prove Goldman Sachs rigged a CDO portfolio against its own clients. The test statistic showed default rates were more than 3 standard deviations from what random selection would produce. Goldman paid $550 million, the largest SEC penalty in history at the time. One framework, 5 steps, that is hypothesis testing, and the CFA exam tests exactly this framework on every single quantitative methods question that asks you to draw a statistical conclusion. The exam tests exactly one thing here. Can you execute all 5 steps in the correct order without mixing them up? Step 1, state the hypotheses. Step 2, choose the significance level. Step 3, compute the test statistic. Step 4, find the critical value or p-value. Step 5, make the decision. Every hypothesis testing question on your exam maps to one of these 5 steps. Memorize this sequence cold. It is your universal template. Step 1 is where most candidates make their first mistake. The null hypothesis H0 is always the statement of no effect, no difference, or equality. The alternative hypothesis H is what you are trying to prove. You never test H, directly, you test whether the evidence is strong enough to reject H0. Critical language rule: the CFA exam never uses the phrase, "accept the null hypothesis." If you see that in an answer choice, eliminate it immediately. The correct phrase is always, fail to reject H0. A not guilty verdict does not prove innocence. Failing to reject H0 does not prove it is true. One-tailed versus two-tailed. This distinction directly controls which critical value you use, and the exam will absolutely test this. A two-tailed test at 5% significance splits alpha equally, 2.5% in each tail, giving a z critical value of 1.96. A one-tailed test at 5% puts all 5% in one tail, giving z equals 1.645. The most common exam trap, using 1.645 when the test is two-tailed or 1.96 when the test is one-tailed. Read the hypothesis statement carefully. If H uses not equal to, it is two-tailed. If H uses greater than or less than, it is one-tailed. Step 3 is the calculation step, and the single most tested formula in quantitative methods. The t-statistic equals the sample mean minus the hypothesized population mean divided by the standard error of the mean. That denominator, s divided by the square root of n, is the standard error, not the standard deviation. The number 1 computational trap on the CFA exam. Forgetting to divide s by root n, if you divide sample mean minus mu0 by s alone, you get the wrong answer. The denominator is always the standard error. When the population standard deviation sigma is known, use the z-statistic instead. The formula looks nearly identical: population, mean mu0 in the numerator, sigma over root n in the denominator. The exam makes the distinction crystal clear. If the problem gives you sigma, the Greek letter, use z. If the problem gives you s, calculated from your sample, use t. Greek letter sigma equals z-test, lowercase s equals t-test. That is the entire decision rule. Sample size does not override this rule. This is the single most important decision rule in hypothesis testing, and competitors consistently get it wrong. The exam tests exactly one thing here. Do you know when to use t versus z? The rule is simple. Use the t-test when the population standard deviation is unknown, which is almost always. Use the z-test only when sigma is explicitly given. The dangerous misconception is the n greater than 30 rule. Many candidates believe that if n exceeds 30, they should switch to z. That rule is for the central limit theorem approximation. It is not the CFA rule for test selection. On your exam tomorrow, if the problem gives you a sample standard deviation s, use t period. Sample size is irrelevant to this decision. Now execute the full 5-step framework with a real exam-style problem. A portfolio analyst tests whether mean daily return differs from zero. Sample of 36 days. Sample mean, 0.15%. Sample standard deviation, 0.45%. Step 1, H0, mu equals 0. HA, mu not equal to 0, two-tailed test. Step 2, significance level alpha equals 5%. Step 3, test statistic. T equals 0.0015 minus 0, divided by 0.0045 divided by root 36. That denominator is 0.0045 divided by 6, which equals 0.00075. T equals 2. Step 4, degrees of freedom equals n minus 1 equals 35. Two-tailed T critical at 5% with 35 df equals 2.03. Step 5, T stat of 2 is less than critical value of 2.03. Fail to reject H0. Insufficient evidence that mean return differs from 0. Step 4 offers a second approach, the p-value method. The p-value is the probability of observing a test statistic as extreme as yours, or more extreme, assuming the null hypothesis is true. The decision rule is simple. If p-value is less than alpha, reject H0. If p-value is greater than or equal to alpha, fail to reject. Small p-value means strong evidence against H0. Large p-value means insufficient evidence to reject. Think of the p-value as how surprising your result would be if H0 were true. The more surprising, the smaller the p-value. The p-value is the most misunderstood concept in all of quantitative methods, and the CFA exam tests this misunderstanding directly. The exam tests exactly one thing here. Do you know what the p-value actually measures? A p-value of 0.03 does not mean there is a 3% probability that the null hypothesis is true. That is the classic wrong answer. The p-value is the probability of observing a result as extreme as yours, assuming the null hypothesis is true. It measures how surprising your data is under H0, not the probability that H0 is correct. If you see an answer choice that says there is a 3% probability the null is true, eliminate it. The correct interpretation, since p-value 0.03 is less than alpha 0.05, reject the null. Type I and type II errors are tested together in every exam sitting. You need both definitions cold and the trade-off between them. Type I error, you reject a null hypothesis that is actually true, a false alarm. The probability of type I error equals your significance level alpha. Type II error, you fail to reject a null hypothesis that is actually false, a missed detection. The probability of type II error is called beta. The power of a test, which the exam also tests, equals 1 minus beta. Higher power means better ability to detect true effects. Here is the trade-off that candidates miss. Lowering alpha reduces type I error, but increases type II error. The only way to reduce both simultaneously is to increase your sample size. Exam question. An analyst tests whether mean daily return differs from 0 using 36 observations. Sample mean is 0.15%, sample standard deviation is 0.45%. The test statistic is closest to a 2, B 0.33, C 0.15. Pause if you need to work it out. The answer is AT equals 0.0015 minus 0. Divided by 0.0045, divided by root 36. Root 36 is 6. Standard error equals 0.0045, divided by 6 equals 0.00075. T equals 0.0015, divided by 0.00075 equals 2. If you chose B, 0.33, you made the most common trap on this topic. You divided sample mean by standard deviation without dividing by root n. The denominator is the standard error, not the standard deviation. Always divide S by root n. Second exam question, this one tests the T versus Z trap directly. Using the same data, T-stat equals 2, N equals 36, two-tailed test at 5% significance. The analyst should A. Reject H0 because 2 is greater than 2.03. B. Fail to reject H0 because 2 is less than 2.03. C. Reject H0 because 2 is greater than 1.96. Pause to work it out. The correct answer is B, with 35 degrees of freedom and a two-tailed test at 5%. The critical t-value is 2.03. Since our t-stat of 2 is less than 2.03, we fail to reject H0. Choice C is the exam trap, using the Z critical value of 1.96 instead of the T critical value. Since sigma is unknown, we were given S, the sample standard deviation, we must use the T distribution. Always T when sigma is unknown, regardless of sample size. Third question, testing power. A hypothesis test has a significance level of 5%. The probability of a type II error is 20%. The power of the test is A 5%, B 80%, C 75%. The answer is B. Power equals 1 minus the probability of type II error. Power equals 1 minus 0.2 equals 0.8, or 80%. Choice A, 5%, is the significance level, which is the probability of type I error, not the power. These are completely different things. Choice C, 75%, comes from subtracting both alpha and beta from 100%. That is wrong. Power is defined strictly as 1 minus beta. Significance level alpha plays no role in the power calculation. Exam strategy for hypothesis testing. This topic is worth approximately 11 to 16 questions across the 180-question exam. You will see at least 2 to 3 hypothesis testing questions requiring calculation. Time allocation. Do the 5 steps in writing on your scratch paper. Do not try to shortcut the framework under pressure. The steps are fast when memorized. 4 decision rules to have cold before test day. 1. Sigma known means z-test, sigma unknown means t-test. Sample size does not change this rule. 2. Two-tailed at 5% uses z equals 1.96. One-tailed at 5% uses z equals 1.645. 3. P-value less than alpha means reject H0. 4. Never write except H0, always fail to reject. If this was on your exam tomorrow, you would get it right. Pause and screenshot this. This is your complete hypothesis testing reference card. Every formula, every decision rule, every critical value you need for the exam is on this one card. The 5 steps: state hypotheses, set alpha, compute test statistic, find critical value or p-value, decide. The T versus Z rule, unknown sigma means t-test always. 2 key formulas: T equals x bar minus mu 0 over s root 10, Z equals x bar minus mu 0 over sigma root 10. Critical values cold: two-tailed 5% Z equals 1.96, one-tailed 5% Z equals 1.645, two-tailed 1% Z equals 2.576, one-tailed 1% Z equals 2.326. Power equals 1 minus beta. Type I equals false alarm. Type II equals misdetection. If this was on your exam tomorrow, you would get it right.